Hi everyone, and welcome back to Neuropsychology. So this is the last lecture for chapter 4. Yay! So in the last video we talked about the action potential, about voltage sensitive ion channels. We talked about the phases of an action potential, which you can see right here. Here's rest, absolutely refractory period, relative refractory period, and rest again. We also talked about how the message gets sent along the axon through saltatory conduction, and this is because of all the myelin around the axons. So in this video, we are going to talk about how the cell gets its information and how this action potential is created. So we're going to talk about EPSPs and IPSPs, which are technically graded potentials. And then we will talk about spatial and temporal summation. And lastly, we will talk very briefly about multiple sclerosis. Okay, so how do neurons integrate information? So we know by now that dendrites are connected to many other neurons, so to many other axons. And what they receive are nerve impulses. So some of these are excitatory and some of these are inhibitory. If they are excitatory, they will depolarize the postsynaptic membrane. So if you forgot the word depolarize, they will make it a little less negative or a little more positive. And we call these graded potentials EPSPs. And EPSP stands for excitatory postsynaptic potential. So an EPSP would literally be this. It is excitatory, so it will make the cell more likely to fire an action potential. It gets a little bit more positive or a little bit less negative, and it's excitatory. So remember, EPSP stands for excitatory postsynaptic potential. They can also be inhibitory, and they can hyperpolarize the postsynaptic membrane. So we talked about this a lot. Hyperpolarization is when it becomes more negative. When it becomes more negative, the cell is less likely to fire an action potential because the threshold is around -50, so it's going away from the threshold. So we call these graded potentials IPSPs, or inhibitory postsynaptic potentials. So definitely don't forget that. IPSP stands for inhibitory postsynaptic potential. So here the membrane gets more negative. It goes further away from the threshold to get an action potential. So it will be less likely that the cell will fire an action potential if you have many of these. Okay, so here I have another little recap. Often when I repeat myself a lot, I find these things important, or the words are just a little confusing, or both, most likely both. So again, excitatory graded potentials or excitatory postsynaptic potentials, EPSPs, they increase the probability of an action potential happening at the axon hillock. So these EPSPs and IPSPs come in from the dendrite and they go to the cell body or the soma, and then they will all add up together. And then if the threshold is reached around the axon hillock, then an action potential will happen or not. So EPSPs are created by the opening of sodium channels. So sodium will go into the cell, and this will make it a little bit more positive. IPSPs are hyperpolarizations, and they are due to the opening of chloride or potassium channels. So either chloride will go into the cell or potassium will go out of the cell. Okay, so here we have a beautiful schematic picture of the cell body. And these are dendrites, kind of cut off, but these are dendrites with incoming messages. Here we have the axon hillock, or the start of the axon. Here we have the axon, and here we have the terminal. Okay, so graded potentials happen mainly on the side of the cell body, and the action potential only happens in the axon. So to produce an action potential, the summated graded potentials, which consist of IPSPs and EPSPs, they are on the cell body and they must depolarize the membrane at the axon hillock to its threshold, so to the negative 50 millivolts. So if this threshold is met, the action potential will be generated. So here you see all these EPSPs and IPSPs, so they will technically be added on to each other. But it's not a simple thing of just adding all the EPSPs and taking off all the IPSPs. It also depends on how far they are from the axon hillock and how large this graded potential is. So the closer a graded potential is to the axon hillock, or the stronger they are, or both, the more likely or the bigger effect they will have on the stimulation of the axon hillock. Okay, so definitely look over this picture, maybe draw it out once or twice. It's a very important picture. So there are two things that are important to create an action potential. We have temporal summation and spatial summation. So temporal summation, technically it means exactly what it is called. So it means that the graded potentials will only be added up to each other if they happen close together in time. So if a positive EPSP happens, or an excitatory postsynaptic potential, and a couple minutes later another one happens, these will not be added up because the first one happened a long time ago and is over. So two EPSP add on to each other, making the membrane potential less negative or more likely to fire an action potential. An EPSP and an IPSP kind of work counteractive, so they could cancel each other out if they're if they happen at the same time and are at a similar location. And two IPSPs will make the membrane potential more negative, so it makes it less likely for an action potential to start. So spatial summation is similar to temporal, but it's just about space. So spatial summation means that two graded potentials that are close together will sum up, and if they are farther together, their graded potential will not reach to have an additive effect. So here's a picture of that. So for example, if these EPSPs, they're both excitatory, if they are produced at the same time, but on total opposite sides of the cell body, they will have no influence on one another. But if you put them next to each other, they will add up. So here you see that they will reach to the red line. And since they're far from each other, there will be one here and one here, but they don't influence each other. But if they're next to each other, you can add them up. So one disorder that has to do with axons and myelin is multiple sclerosis. So multiple sclerosis is a degenerative nervous system disorder, and it attacks the myelin coverings on the axon. So this causes inflammation of the myelin patches and often destroys parts of the myelin. And we now know that myelin is very important for the speed of processing. So eventually a scar or a plaque will form in place, and we call this sclerosis. So that's why the disorder is called multiple sclerosis. And sclerosis is a Greek word for hardness. So of course, if there's less myelin, there will be a disruption of the flow of neuronal information. So the cause of MS is unknown and often is diagnosed between the ages of 15 and 40. And there are a broad variety of symptoms, which include muscle stiffness, vision disturbances, and also short-term memory problems. So here's a schematic picture of that. So here you see a normal fiber with the beautifully wrapped myelin. So in multiple multiple sclerosis, it attacks the myelin. So the myelin is damaged, and often it forms thick hard plaques, and the fiber will be exposed. So there will be a disruption in neuronal information processing. And this was the end of chapter 4. So I will see you guys back soon for the next chapter.